So the laws of logarithms then, in page, around about page 100 in your textbook is where these laws of logarithms are, but don't worry about that at the moment. We need to know these laws of logarithms, just like we need to know the laws of indices. So it's a good idea to have them written down somewhere useful so you can make use of them. The most important one, the one that we're going to focus on once we've talked about them, is this third law of logarithms. That turns out to be one of the most useful ones, particularly when we come to look at power functions and exponential functions, which we're coming on to. So first of all, then, what is a logarithm? Logarithms are powers. Pure and simple. So that's why I'm looking at them with these laws of indices, and we'll see that there's a big connection between the laws of indices and the laws of logarithms, because both of them are to do with powers. Ten to the power x is 3 might be a problem that we want to try and solve. We want to know what power of x have I got to raise 10 to give me 3. And the logarithm allows us to do that. If I find the logarithm of 3, that tells me the power to which I've got to raise a base number, and in this case the base number is 10, so it's telling me what power I've got to raise 10 to get 3. And you've got a button on your calculator that will do that for you. So log to the base 10 of 3 is 0.477, one more significant figure, 1. Okay. The log button, just on your calculator, just says log. It doesn't say the 10 underneath. So if somebody asks you, or you see written down, the log of 3 is 0.4771, that's taken as read that the base is 10. A bit like if we say the square root, we don't bother to put the 2 in. Logarithm without a base written on it means log to the base 10. There must be a base because a logarithm is a power. 0.4771 is a power. This is the power of 10. In this case, it's the power of 10 that gives 3. So what's a logarithm? It's a power of a base, usually base 10. Certainly on the calculator, it's always base 10. So we can use logarithms to turn any number. For example, we've used it to turn 3 into a power of 10. So instead of writing 3, we can write 10 to the power 0.4771. And you might legitimately ask the question, why? Okay. We do this, we turn numbers into powers to allow us to use these laws of logarithms. If we look at the laws of logarithms, the log is a power. So if I take two numbers, a and b, and turn them into logarithms, instead of multiplying them, I add them. Because if you remember from the laws of indices, what do I do with powers when I multiply? Add them. I've turned these numbers, a and b, into powers. So now I find the logarithm of a, turn it into a power, the logarithm of b, turn it into a power, and add them together. Similarly, instead of dividing a by b, I find the log of a and the log of b, which is turned them into powers, and subtract, because when I divide, I subtract the powers. So these first two laws of logarithms come directly from the laws of indices. I said that this one was the most useful, and here's the reason why it's the most useful. It's because I can turn a power into a multiply, and we use that to solve equations where the unknown is in the power, as we'll see in a second. And so that's the real use of these logarithms, and that's where we're going to use it using almost exclusively this law of logarithms, although we'll find these first two come in as well when we're trying to simplify things. But the real power of these logarithms is in this third law of logarithms. So let's look at an example of how that can be useful. There's a problem. And again, as we looked at one earlier, you don't need to write this down if you don't want to, because it's in the textbook. In that chapter I just highlighted for you on logarithms. Solve this equation, correct to four significant figures. 2 to the power x equals 3. It's an equation. So what I do is, whatever I do to one side of the equation, so long as I do it to the same to the other side of the equation, I've not changed anything. So what I do is, I take my 2 to the x and find the logarithm of it. Logarithm of 2 to the x. Equals the logarithm of 3. I'll log both sides. We say log both sides. In other words, take the logarithm of both sides of the equation. So long as I do the same, if I want to do something to one side of the equation, so long as I do it to the other side, it's still true. That left-hand side still equals the right-hand side. All I've done now is turn them into powers by taking the logarithm. If you look at the third law of indices that we've just written down, that's telling me if I've got the logarithm of a to the power n, this becomes n times the logarithm of a. And it actually comes from, if we just zap back to the laws of indices, which are at the beginning of today, here, it comes from this directly. This one here. A to the n. I've got one base raised to a power, raised to another power. So if I've got one power raised to another power, I multiply. That's the key. I've turned a number into a power by making it into a logarithm. And then it's one power multiplied by another. And so I'm turning a power into a multiplication. And that's what the third law of logarithms is saying. I'm labouring this point a bit, but I want to try and make it clear. So we're using, this is the key, this third law of logarithms. So what we do is we say, in that case, and this is where it becomes apparent, instead of this x being in the power, it comes down and turns into a multiplier. And we've got x times the logarithm of 2 equals the logarithm of 3. So by taking logarithms, I can bring my x down and it becomes a multiplication because of these laws of indices, laws of logarithms. And now all I have to do is divide both sides. It's a straightforward equation now. X is multiplied by a number. Log 2 is a number. I could work out what it was on the calculator. So if x is multiplied by that number, divide by it. So x equals log 3 over log 2. And now I get my calculator out and work out what x is. So we get 1.585 to 4 significant figures. It's worth holding on to a few significant figures because remember these are powers of 10, so a small change in the power makes a big difference to the number because it's a power. So hang on to some significance if you need to write it down, hold 4 or 5 significant figures. So x equals 1.585. Like any good engineer, you would want to now check this is right because you're in your workshop and this is part of a calculation that you're doing, some calculation. You've got no one there to say, yep, that's right. So you need a way of checking. Go back to the original equation. In theory, if you're right, 2 to the power x should equal 3. So to check, 2 to the power 1.585 should equal 3. Does it? Slightly more complex equation, but still the same start point. you say to yourself, x is in a term, but x is in the power. So the term involving x I'm trying to find is in the index, is in the power. So it's always the first step. If that's the case, I take logarithms of both sides. So the first step is logarithm of 2 to the power x plus 1 equals the logarithm of 2x minus 5. Sorry, 3 to the 2x minus 5. Because I've turned this into a power now by taking the logarithm, the x plus 1 from the third law of logarithms can come down and become multiplied. So this becomes x plus 1 times the logarithm of 2 equals 2x minus 5 times the logarithm of 3. And when you're confident with these things, there's nothing to stop you jumping straight to this step, because by taking logarithms of both sides, that automatically means I can bring the power down and turn it into a multiplier. So I'm quite happy for you to jump straight to that step. At this stage, then there's 2 or 3 different things we can do, and if you think about it, you can make life a bit easier for yourself. Log 2, as we know already, is quite a long decimal number, and we can hold 4 or 5 significant figures, and so is log 3, 4 or 5 significant figures. So if at this stage I multiply out the brackets on the left and the right, I'm going to have quite awkward numbers in here, or I'm going to have to leave it as log 2. It makes it a bit more long-winded. At some point you have to work out what log 2 and log 3 is. So divide both sides. If I divide both sides by log 3, I'll get rid of the log 3 here, and I'll have it over log 3 here. Or I could divide both sides by log 2 and get rid of that log 2 there, and then divide by log 2 over here. The question is, which is going to make it easy for myself? I look at it and I say, well, eventually I'm going to have to multiply out either this side of the equation or that side of the equation. To me, that looks a little bit easy to multiply out because it's only x plus 1. So I was going to divide both sides by log of 3. And that's probably the easiest way to go about doing it. I could multiply out the brackets, or I could divide the other side. It'll all work, but if I divide by log 3, it's probably the easiest. So divide both sides by log 3. X plus 1 log 2 over log 3 equals 2x minus 5. I don't need the bracket anymore because the log 3 is gone. Now you can work out what log 2 over log 3 is on the calculator. Could call it maybe 0.631, but remember it's a power of 10, so a small change in this power will make quite a big difference to the number. Equals 2x minus 5. Now I can multiply out the brackets, and now we can see how easy it is to multiply it out. So I get 0.6309x plus 0.6309 equals 2x minus 5. And now we've got a linear equation to solve. We get all the terms involving x on the same side. So what do? I multiplied 0.639 by x to get 0.639x, and then 0.639 times 1 is 0.6309. Okay? And now we're going to get all terms involving x on the same side, so subtract 0.6309x from both sides. So that will leave us 0.6309 over here. What's 2 minus 0.6309? 1.3 something or other. 1.3691, is it? I might be wrong. Yeah. X minus 5. And now let's get rid of the minus 5 on the right hand side by adding 5 to both sides. So 5.6309 equals 1.3691x. And now finally divide by 1.3691 to get x. Which gives 4.113. How do we check that was right? How do we check? Yeah, that's right. Go back to the original equation, put in your value for x in here, and work out what 2 to the x plus 1 is. And work out what, exactly that, work out the other side and see if you get the same answer, and then you know you've done it right. Okay? Yeah. Always do a check. So now turn to page 103 in the textbook. Exercise 54 on indicial equations. Try some of those. If I give you about 10 minutes, quarter of an hour or so on that, that will take us roughly to the end of the session. So give us a minute just to round.